And we're moving on to the advanced problem. If there is no seasonal effect on human births, we would expect equal numbers of children to be born in each season: winter, spring, summer, and fall. A student takes a census of her statistics class and finds that of the 120 students in the class, 25 were born in winter, 35 in spring, 32 in summer, and 28 in fall. She wonders if the excess in the spring is an indication that births are not uniform throughout the year. Question A asks, what are the null and alternative hypotheses associated with this question? Well, you're looking for the relationship between two things: human births and the seasons. So the ho would be that there is no association between human births and the seasons. And the ha is that there is an association between human births and the seasons. And if we were to make some sort of a table, this is what it would look like. B, compute the chi-square statistic. All right, so first, you have to understand that you're using a chi-square because you have a matrix. You have a 4 by 1 matrix. And to do this, you need the expected value, because this 25, 35, 32, 28 are the observed values. You would need the expected. So why did you get 30 for all of them? Well, it's really simple, actually. It says we would expect equal numbers of children to be born in each season. Equal number of children. And we had a sample of 120. So if there's 4 seasons and 120, and if we divide it by 4 equally, then we have 30 in each season. Make sense? Okay, so you have your observed and you have your expected. So now you can use this chi-squared equation, which is the sum of the observed minus expected squared over expected, and you get 1.93 repeating, or 1.9333. Or you could use a calculator. And to do this, you have to use something called the the chi-square test for goodness of fit, which is GOF right here. Now, first of all, you need to go to stat edit and plug in your observed value and expected value. After you've done that, like I said, you go to the goodness of fit. Here it is. And then L1, L2. Degree of freedom is 3. Okay, so you know that it's n minus 1, right? Well, Taejong, the n is 120, so shouldn't it be 119? No, for the chi-squared, that n is the number of the observed values that you have, the number of proportions that you have. Since you have 4, it will be 4 minus 1 and 3. So if you calculate that, 1.9333, exactly the same. And that's how you find the chi-squared value. Going back to B, you're using a goodness of fit test, not a regular chi-squared test, because you're given, well, just think of it like this. If you have one column of things, like one column, you use the GOF, goodness of fit. And that's when we would have to find the expected value and such and such. And as I previously explained, I answered C already. You have a degree of freedom of 3, because if you look at the rows, these are the rows, right? There's 4 rows. And so it's pretty much row minus 1, I guess, if you think of it that way. So n minus 1, there's 4. 4 minus 1 is 3, and that's your degree of freedom. D, what do you conclude about the null hypothesis at alpha equals 0.05? All right, so do you reject the ho or do you not reject the ho? Taejong, you've done this a million times now. What do you need? That's right, you need that p value. Okay, so, well, we plugged everything in, the GOF test, and we got the p value of that, 0.5864. And since that's greater than 0.05, we fail to reject the null hypothesis, the ho, that there is no association between human births and the 4 seasons, based on our p-value of 0.5864 being greater than the alpha value of 0.05.